All right, welcome back to linear algebra. Let's jump into Anki. Le 11 flashcards. How many different inverses can be invertible? Can an invertible matrix have? 1. What is an invertible matrix, and what is another name for such a matrix? Another name is non-singular. What is an invertible matrix? It's a matrix in which another matrix exists in which A times B is equal to B times A is equal to I. If R is the reduced row echelon form of a square matrix, and R has 0 rows, then what must be true of matrix R? If R is the reduced row echelon form of a square matrix, and R has no 0 rows, then what must be true for matrix R? Is equal to the identity matrix, or I. What are the commutative law of addition for addition? I mean the associative law for addition, associative law for multiplication, left and right distributed laws for matrices. Commutative law for addition, A plus B equals B plus A. Associative law for addition, A plus B in parentheses plus C is equal to A plus B plus C in parentheses. The associative law for multiplication, A times B within parentheses times C is equal to A, and then within parentheses B times C. Left distributive law for matrices, A times the sum of B plus C equals AB plus AC, and the right distributive law for matrices, the sum of A plus B times C is equal to BA plus CA. What are the non-trivial solutions, if any, of a homogeneous or homogeneous linear system in unknowns? Why is it if any? What are the non-trivial solutions, if any, of a homogeneous linear system in the unknowns? X1, x2, and xn. Xn. The solutions are basically anything in which all the unknowns do not equal 0. Any solutions that is not the trivial solution, which is all of them equaling 0. If A is an invertible matrix, how is the transpose of its inverse related to the inverse of the transpose of A? The inverse of A, the transpose of inverse of A is equal to the inverse of the transpose of A. Is it true that the inverse of A equals 1 divided by A if A doesn't equal 0? No, because matrix division is not a defined operation. It is not true in general that a matrix product AB is the same as the matrix product BA. State 3 ways in which the equality can fail to hold. B and A and B and B and A are different sizes. A and B and B and A are one is defined and one is undefined, and another one is A and B and A are the same size, but the corresponding entries are not equal. How is the transpose of a product of matrices related to the transpose of the individual factors? The transpose of a matrix, transpose of a product of matrices, and the transpose of individual factors. Okay, so the product of the transpose of the product is going to be equal to the transpose of the individual factors, except in reverse order. If A, B, and C are matrices for which AB equals AC and A doesn't equal 0, does it follow that B equals C? No. In general, the cancellation law doesn't hold for matrices. Matrix multiplication, that is. Man, some lag and stuff, and Anki really messes this stuff up. Is it possible to get a zero matrix by multiplying two non-zero matrices? Yes. All right, that's it for the flashcards. Crazy, since the day I started Anki, I've had 44% of the days I've spent learning, even though there's been massive blocks of breaks I've taken, month breaks, multiple times. Crazy. All right. All right. I'm gonna grade what I did yesterday, and then I'll be back to recall in a second. All right, we got the problem right from yesterday, and I'm gonna jump in and do more problems right now. All right, we finished the problem from 1.3, review problem in which you have a 4x4 matrix, and you want to satisfy that A sub ij equals I to the j minus 1, and so this is what we got. Elementary, what is this? Showing that if these were unknowns, A, B, and C, that at least there has to be 1 0 in this row if it's an elementary matrix. So if it's an elementary matrix, we know that it starts with an identity matrix, and you do one elementary row operation. So there's only 3 elementary row operations. The first, you can swap the rows. That's always going to guarantee you have at least 1 0, or you're going to have 2 zeros in the bottom, actually, because if you swap any of these rows, they all have 2 zeros. So you'll always have 2. If you multiply one row through by a non-zero constant, you're going to have 2 guaranteed in the bottom row. And if you add a multiple or a constant times one row to another row, you're still going to have a guarantee at least 1 0 in the bottom row. And then now we're trying to work through a proof. A little more difficult. It feels uncomfortable to do a little bit, but that's a good sign we're learning. Basically, we're trying to prove if A and B are MXN matrices, then A and B are row equivalent if and only if A and B are the same have the same reduced row echelon form. Okay. So what do we need to show? We probably need to show that if matrices A and B are the same size, then A and B are row equivalent if A and B have the same reduced row echelon form, and if A and B have the same row echelon form, then they are row equivalent. So I've been just trying to brainstorm through this. What does row equivalent even mean? Row equivalent means you can derive one matrix from the other and vice versa with only using elementary row operations. A reduced row echelon form only has 1 per matrix. That's just the definition, by part of the definition. So just some of my brainstorming, if A and B are MXN matrix, then they're the same size, and they're row equivalent if you can get one from the other using elementary row operations. That's the definition of row equivalency. So this is also the same as saying as multiplying a sequence of elementary matrices by A can get you B. Then if you can turn A into B, B equals B, and B only has 1 reduced row echelon form. So that's just kind of some brainstorming, but I think I realize it's an if and only if, so I should show it works forward and it works if you flip the hypothesis to the conclusion. So I'll work on that tomorrow. But yeah, that's it for today. Talk to you tomorrow. See ya.